In the previous lecture, we have started to deal with the molecular field theory of antiferromagnetism. Actually, we have discussed the first part of this molecular field theory of antiferromagnetism, and you have seen that how the magnetic susceptibility of a antiferromagnetic crystal varies with temperature uh, when the temperature is greater than Neel temperature. Okay. Now today we will see the same problem, but our discussion will be for temperature which is lower than Neel temperature. Okay. Actually, you have seen that in this molecular field theory, we have to consider a body-centered cubic structure of antiferromagnetic material. And this structure, as you can see in this first figure, consists of actually two interpenetrating sub-lattices. So this is also called two sub-lattice theory. Okay, and those two sub-lattices are A and B. Okay, and you can see that the spins of A and B are just anti-parallel to one another. And in this second figure, I have shown the variation of the magnetic susceptibility of antiferromagnetic material in again stop temperature T. Okay. Now, as I have told you that the present concern of ourselves are actually the calculation of magnetic susceptibility of this antiferromagnetic material when the temperature is lower than Neel temperature, that is T is less than Tn. Okay. Actually, this calculation depends on the orientation of magnetic field, in which direction magnetic field is directed, that is what is the angle between the applied magnetic field and the magnetic spins, that actually decides the value of magnetic susceptibility. Actually, I am suffering from cold, so don't mind that my sound is not very clear, but this lecture is necessary to uh, actually publish, so I am recording it. So don't mind, because I am suffering from a severe cold. So, as I have told you that actually the calculation of magnetic susceptibility depends on the orientation of the magnetic field, that is the angle made by the external magnetic field with the magnetic spins. But for in this case, we will consider the two important directions of the applied magnetic field. First of all, we consider the magnetic field is perpendicular to the axis of spins. It means H is perpendicular to both MA and MB. Okay. And the second important case which we will see is the case that magnetic field is parallel to the axis of magnetic spins. Okay. So in these two situations, we will calculate the magnetic susceptibility, and we will also learn how this magnetic susceptibility varies with temperature. Okay. Actually, in this case, for simplicity, we consider only the AB interaction. It means the interaction between the dissimilar atoms we will consider. And for simplicity, we neglect the interaction between similar atoms, that is AA interaction, BB interaction will be neglected. And as you know, you have learnt in the previous lecture that for the AA interaction and BB interaction, the interaction constant or Weiss constant is lambda II. Since we are neglecting this interaction in this case, so this lambda II will be taken equal to 0. But as you have assumed that the interaction of AB type, that is different interaction between different atoms, is active. So in this case, this lambda ij is not equal to 0. So we will take it as equal to lambda, because now there is no need to write down the suffixes, because there is only one interaction constant, so we will simply write it lambda. Okay. Now, as I have told you that we will consider two situations. In first situation, we consider that the applied magnetic field is perpendicular to the axis of spins, and in second, when the magnetic field is parallel to the axis of spins. Okay. So now let us see first of all the calculation of magnetic susceptibility of antiferromagnetic material when H is perpendicular to MA or MB. Okay, on both. And for this, let us see this figure. Actually, here I have shown that the initial direction of MB is this direction, and the initial direction of MA is this direction. That is the spin of A, or the magnetic moment due to a spin of A is directed in this direction, and that of B is directed in this direction, and the field is perpendicular to both of them. Okay. Actually, when you will apply this magnetic field, then due to the interaction of the field with the spin, when you say spin, that just behaves like a magnetic dipole. So the dipole will experience a torque, and due to that torque, the dipole will tend to align themselves along the applied magnetic field H. But this alignment is not completed. In equilibrium, let us consider that the spin A, which is MA, is making an angle phi with its initial direction, and that B, that is MB, is making an angle phi with its initial direction. Actually, we consider that both MA and MB are equal, and so you can see that both will be rotated by the same value of angle, which I have assumed pi. Okay. Now, as the spin system A and B have been turned by the applied field by angle phi, so the molecular field acting on B will be equal to what? When you talk about molecular field, you have learned in the first part of the lecture that the effective magnetic field at the site of spin A, which is written by the symbol HA. HA is in fact what? This is the effective magnetic field at the site of spin A. And that is equal to, you have seen earlier in the first part of the lecture, this is equal to H minus lambda II times MA minus lambda IJ times MB. Okay. And in the similar way, you have also seen that the effective magnetic field at the site of spin B, denoted by the symbol HB, is given by H minus lambda IJ MA minus lambda II MB. Okay. Lambda II MB. We have seen earlier. Now here we are in this expression. What is this lambda II MA? This is actually the molecular field, internal molecular field, due to the interaction between AA or BB. Okay, BB spins, and this lambda IJ MB, this is the molecular field due to the interaction between the spin A and spin B. Okay, but as we have assumed that only the AB interaction is effective, not the AA or BB. So you have assumed here that this interaction constant lambda II is 0. So actually this lambda II and this lambda II both will be equal to 0. Okay. So at the site of spin B, what is the molecular field? Since lambda II is 0, so the molecular field is only this much. This is molecular field, intermolecular field. So you can, and lambda IJ, you have considered that this is equal to lambda. So the molecular field at the position of spin B is equal to simply minus lambda times Ma. This is molecular field. We are not talking about the effective field Hb. We are only talking about the internal molecular field. Okay. Now you can see this in this figure that this is minus lambda Ma because Ma is a vector and lambda is a positive scalar. So minus lambda Ma will be just in opposite direction of Ma. So from the geometry of figure, it is obvious that this angle is also equal to phi. Okay. Now the component of this minus lambda Ma on the line of the applied magnetic field H, this will be what? That will be minus lambda Ma times sine phi. Sine phi. This will be the component of this minus lambda Ma on this on the line of H, that is in this downward direction. Okay. So you can see I have written that the molecular field acting on B in a direction parallel to H, that is minus lambda Ma times sine phi. But as phi is very small, and you know if angle is very small, sine phi is simply equal to phi, and therefore you can write only phi at the place of sine phi. So this component of molecular field acting on B in a direction parallel to H is equal to minus lambda Ma phi. Okay. Now in the similar manner you can see this minus lambda Mb, this is the molecular field at the site of this Ma, at the site of Ma, and its component on the line of H will be again minus lambda Mb phi. Okay, you can see. So the total total molecular field on the line of H will be the sum of these two components, and that will be 2 lambda Ma phi, because Ma is equal to Mb. Ma is equal to Mb, so you can write this equal to 2 Ma phi. I have not written the minus sign here. This is obvious that this minus sign indicates that this is just in opposite direction of the applied magnetic field. Okay. So you can see the total molecular field opposite to the direction of H. This is lambda Mb phi plus lambda Ma phi, but Ma is equal to Mb. So I have written it, this is 2 lambda Ma phi. Okay. But in equilibrium, this 2 lambda Ma phi is equal to H. Okay. In equilibrium, net field along the line of applied field will be 0. So this intermolecular field cancels the applied field in equilibrium. So at equilibrium, you can write this much. Okay. Now, the total magnetization along the line of external magnetic field, what will be that? You can see the figure that if you talk about the total magnetization along the line of H, you have to take the component of Ma along this H and component of Mb also along this line. And it is obvious from this figure that these components will be Ma sine phi. Okay. And the component of Mb along this H will be Mb sine phi. Okay. But again you can see that this Ma and Mb are equal, and so we will write Ma instead of Mb. Okay. So the total magnetic field, total magnetization along the external field direction will be Ma sine phi plus Mb sine phi, and that will be Ma plus Mb times phi, because sine phi is equal to phi, since phi is a very small angle. Okay. But as you know that Mb can be written as Ma, so this total magnetization is equal to 2 Ma times phi. Okay. Now, for getting the value of magnetic susceptibility, we will use this equation 3 in this equation 2. You can see here there is 2ma times phi, but you can see equation 3, this 2ma times phi is equal to m. So instead of this 2ma times phi, you can write what? You can write m. So this lambda m will be equal to h. You can see this equation 2. Okay. And therefore m over h, that will be equal to 1 over lambda. But what is this m over h? You know, this is just the definition of magnetic susceptibility. The ratio of m and h is called magnetic susceptibility. But we are considering the case when the applied field is just perpendicular to the spin's axis. So I have written it chi perpendicular. The sign of perpendicular has been taken as a subscript, just to indicate that we are considering the case when h is perpendicular to MA or MB. So how easily we can find the magnetic susceptibility and this chi perpendicular in this case, you can see. And I hope you have clearly understand this calculation. Okay. Now you can see this is a very interesting result that there is no term contained in the RHS of this equation which will depend on temperature. So it is a very remarkable fact that when we consider the magnetic susceptibility when the applied field is perpendicular to the axis of the spin, that magnetic susceptibility is independent of temperature. It means even at 0 Kelvin temperature, its value will be 1 by lambda. And this remains 1 over lambda when up to t equal to Tn, because we are considering the case t less than Tn. So mark it. Don't think that this this chi will remain same when t is greater than Tn. When t is greater than Tn, then what happens? You have already learnt in the first part of the lecture. So this result holds only when t is less than Tn. So you can say that the magnetic susceptibility in this case remains constant, and that is equal to 1 over lambda from t equal to 0 to t equal to Tn. Actually, we will show this fact by a proper graph, and later on you can see. Okay. Actually, in the calculation of this result, a very important fact has been neglected. Actually, there is also an anisotropy field which developed due to the anisotropic behavior of the crystal. But in calculation of magnetic susceptibility, till now we have not considered such a field. So actually, when we have to make a rigorous calculation or rigorous treatment for the calculation of this magnetic susceptibility, then you have to consider this anisotropy field. And when this anisotropy field is considered, then it is found that this chi perpendicular is equal to 1 over lambda plus h anisotropy divided by 2ma. I have actually written this result directly without any proof. For examination purpose, you have to remember it and write down in your answer directly, because its calculation will be very lengthy. That is not needed. Okay. And actually, according to this result, we will see later on, this chi perpendicular also depends on temperature. So the simpler result which we have obtained neglecting the anisotropy field, that indicates that field is the magnetic susceptibility in this case is independent of temperature. But you will see later on that the rigorous treatment of this problem due to which we obtain the expression for this chi perpendicular in this manner, that indicates that this chi perpendicular is also temperature dependent. how it varies with temperature we will see later on. Okay. So I have written it here. You can see that this H Aries is a field which by itself tends to keep the spins in the natural spin direction, that is anisotropy field. Okay. So this is all about the first case when we have considered that the magnetic field is perpendicular to the axis of the spins. Okay. Now we will consider the second case in which we will see that H is parallel to MA or MB. As you can see in this figure, I have shown that this MA is in just opposite direction of the applied field H and MB is parallel to it. Okay, because MA and MB in general is in opposite directions in case of antiferromagnetic material. Actually, the calculation of this magnetic susceptibility in this particular case is very tedious. Okay, or you can say that calculation of this chi parallel corresponding to an applied field along the axis of spins is much complicated. So actually I have not made that calculation here, that is not needed for your examination purpose. You have only to see the discussion or the or that result obtained from this for this case by Van Vleck and remember some of the important facts of this case. Okay, so as you can see, the calculation for the magnetic susceptibility chi parallel was due to Van Vleck on the basis of a very rigorous theory. Okay, but I have not discussed that theory here. But what we actually gain from that theory, what we actually obtain from that theory, I have discussed here. You can see in this figure that I have shown a graphical plot of chi in against of T over Tn. Okay, and this graphical plot is not for only the second case, but I have shown here the variation of chi perpendicular to in against of temperature. Okay, you can see that at as the temperature increases, you can see that susceptibility rises smoothly from zero. See here, from 0 to a particular value corresponding to the Neel temperature. Actually, corresponding to this point P, temperature is equal to Neel temperature. So I have written here T over Tn is equal to 1. It means corresponding to this point P, temperature is equal to Neel temperature. Okay. Actually, in this case, at absolute zero, you can see all the spins are parallel or anti-parallel to the field, so that no torque is exerted over them. You can see this figure, and consequently there is no net magnetization. It means that at T equal to 0 Kelvin, chi parallel will be 0. Okay, so this curve is for chi parallel. You can see it here. So chi parallel is equal to 0 when T is equal to 0 Kelvin. Okay. Actually, in this figure, I have shown the theoretical variation of susceptibility of an antiferromagnetic single crystal with temperature for the spin values 1 by 2. This curve is for J equal to 1 by 2. This curve is for J equal to 3 by 2. And this curve is for J equal to 5 by 2. And you can see that after some increase of temperature, all these curves coincide, and this becomes maximum at point P corresponding to the Neel temperature. Okay. Actually, from this graphical plot, we can observe some of the remarkable facts. First of all, see this equation you can see this equation A2. Okay, actually when when temperature is decreased, this Ma will increase, T decreases, okay, D for decreases, and Ma will increase, I for increases. And if Ma increases, this second term will decrease. So as a whole, you can say that numerator will decrease. And if numerator will decrease, this chi perpendicular will increase. It means on decreasing temperature, the value of chi perpendicular increases. Okay, so I have marked it here. You can see that it can be seen that since Ma increases as T decreases, okay, and increasing the value of chi perpendicular with decreasing temperature is obtained. Okay, now see the another remarkable fact from here. You can see the this equation, equation number A1, where chi perpendicular has been defined not by rigorous calculation, neglecting the anisotropy field, and you can see that this chi perpendicular is 1 over lambda. This is independent of temperature. So this value of chi perpendicular will remain constant from 0 Kelvin to temperature Tn, which is called Neel temperature. So this chi perpendicular marked here, you can see that this is actually equal to constant up to Neel temperature. Okay, up to Neel temperature. So this is the another remarkable fact. So you can see that we find that this chi perpendicular should be constant below Neel temperature, and it is equal to the value of Neel temperature, which is also the value at 0 Kelvin temperature. So from 0 Kelvin to Neel temperature, it has a particular value, it has a constant value. Okay, now let us see the third important fact. The third important fact, you can see that this chi parallel, when you say that chi parallel, this rises as the temperature rises from 0 to its value at the Neel temperature Tn. Okay, the zero value of chi perpendicular at T equal to 0. Why it is 0 at 0 Kelvin temperature? You can think what is the physics behind it. Actually, the zero value of this chi perpendicular at T equal to 0 is due to the reason that at T equal to 0, the internal field is so strong that it prevents the spins of one sublattice from turning over into the direction of the spins of other sublattice. Despite that, the field H, which is parallel to one of the sublattices, is acting. Okay, so at 0 Kelvin temperature, this chi parallel is equal to 0. Now, actually, in this figure, chi is the susceptibility for the general case. You can see this figure. This is the susceptibility for general case, not for a specific direction of H. Okay, and at and above Tn, it is independent of the direction of the field. Okay, you can see that what is the direction of the magnetic field that does not decides its value when T is greater than Tn. This part of the curve actually corresponds for T greater than Tn, and this is for the general value of chi, not a particular case. Okay, so in this way we have seen the basic features of the magnetic susceptibility variation with temperature when you apply the magnetic field parallel to the axis of speed. Okay, and we have also discussed the case when the magnetic field has been applied perpendicular to the speed axis. So after this lecture, Now the molecular field theory of antiferromagnetism has been completed. So, comprising these two parts of lecture, the whole theory of antiferromagnetism, which is called molecular field theory, is now complete. And I hope you have definitely enjoyed this lecture. And this is very important for your examination purpose. So, watch the video seriously, write down these things in your notebook. That will be very helpful for you. Okay, thank you very much.